Welcome to Population Health, Big Data, Interoperability, and Analytics for Population Health. This is Lecture C. This component, Population Health, discusses the application of informatics and informatics methods in population health management. This unit, Big Data, Interoperability, and Analytics for Population Health, explains the challenges and opportunities of developing predictive analytics for population health. The objective for this lecture is to describe methods and tools commonly used for population health analytics. Note that this unit does not explain the details of predictive modeling techniques. Please refer to the dedicated component on data analytics to learn more about predictive modeling and analytics in general. This lecture discusses the common approaches used by population health analysts. This diagram shows the overall steps involved in developing analytics for population health management and risk stratification. As shown in Box 1, the first stage involves the merging of various datasets and developing a centralized or distributed population health data warehouse. The second step, depicted by Box 2, includes various processes to prepare the data for analysis, such as fixing data quality issues, deleting or imputing the missing data, and transforming the data to meet the assumptions of a given analytical approach. The next step contains the development of the modeling and data mining approaches. As depicted in Box 3, this step usually requires a base data set and an outcome data set that would collectively include the dependent and independent variables. As illustrated in Box 4, the next step contains the model's validation and evaluation process. In this phase, the analysts use various statistical and data mining concepts to measure how good the model is in differentiating the outcome variable, and how reproducible it is when used on other datasets. As pictured in Boxes 5 and 6, a critical step after an acceptable model is developed is to apply it within the context of a population health management workflow. As marked by Circle C, this lecture discusses the common methods used to develop population health predictive models. Other phases of the population health analytic process are discussed in other lectures. This lecture will cover some of the common methods to explore, classify, compare, and predict population health outcomes. Data exploration is one of the most important steps in developing predictive models for population health. Indeed, data exploration provides analysts with important information about the underlying population health data, such as a deeper understanding of how data is structured, a clearer view of what the potential limitations of the data are, and a better perception of what the potential relationships between dependent and independent variables could be. This section will cover some of the common methods to explore population health data. A simple approach to visualize population health data is to construct a histogram of each of the variables. For example, if cost is the outcome variable, a histogram can quickly inform the analyst that cost is not normally distributed in the population. This histogram shows the distribution of cost in a large insurance claims database. As evident by the histogram's first bar on the left, a large denominator of the population has minimal cost. Also, the histogram shows that there are fewer and fewer patients as the cost increases from left to right. Indeed, there are only a handful of patients with an annual cost higher than $100,000. A summary statistic included on the top of the histogram also shows the fact that the cost data is highly skewed and has a very long tail. This extreme skewness makes the distribution of the data incompatible with the requirements of common predictive methods, such as linear regression models. As discussed earlier in this unit, data transformation is sometimes a critical step to prepare the data for analysis and modeling. Due to the skewness of cost data, as shown in the last slide, the cost data is being transformed by a log function. The result of that log function is depicted in this diagram. As shown, when cost data is log transformed, the cost data becomes more normally distributed, thus making it more suitable for methods such as linear regression, that require such distribution in the underlying data. A box plot can also be very informative to detect the distribution of the underlying population health variables. The log transformation of cost, as discussed in the previous slides, is shown by box plots in this figure. The left box plot shows the long tail of cost, while the right box plot shows the more distributed log transformed version of cost. Note that a considerable number of outliers, represented by the dots at the two tails of the box plot on the right, still remain after the log transformation. This figure shows the methods used to explore the distribution of age in a population health data warehouse. The histogram shows a relatively normally distributed age in the underlying population, which is also confirmed by the box plot and the summary statistics on the right side. This figure is replicating the same exploratory methods and diagrams as the previous slide. However, it splits the age based on gender. As depicted by the histogram, it is obvious that this population has a higher number of females in a large number of age ranges. The box plot shows that, despite the difference in the number of females versus males, the age means and quantities of both genders are very close. The summary box on the far right shows the numerical values of mean age for each gender. Scatterplots are extremely useful in visualizing the relationship of two variables, especially when both variables are numeric and continuous. This scatterplot shows the relationship between age and log transformed cost. Indeed, each point on this scatterplot shows one patient of the selected population cohort who has been extracted from a large claims database. Note that genders are also represented by different colors in the scatterplot. Box plots can also show the spread of a grouped variable against a continuous variable. The box plots presented on this slide show the distribution of log transformed cost in each of the given age groups. Indeed, the box plots show the higher age groups seem to have higher costs overall. However, the statistical significance of such a relationship should be established using appropriate statistical methods. Scatterplots can also be constructed to show the relationship of current cost of a given population with the future cost of the same population. As shown in this diagram, it seems that there is a linear relationship between these current and future costs. Note that genders are represented by different colors in the scatterplot. As noted earlier in this unit, high multicollinearity of independent variables defies the assumptions of certain predictive methods, such as linear regressions. Constructing correlation matrices will help analysts to decide which of the independent variables should be excluded from the model. This specialized diagram shows the correlation of all potential variables included in a population health model. The size of the pie shows the amount of the correlation, while the color of the pie shows the direction of the correlations, either positive or negative. As depicted in this diagram, there seems to be a higher than usual correlation between current cost and primary care physician visits, as well as a number of diagnostic counts. Data classification methods can be useful to reduce the dimensionality of population health data. For example, clustering methods can be used to find similar denominators of a population for a given list of variables. This diagram shows a scatterplot of log transformed current cost versus log transformed future cost of a given population denominator. The automated clustering method has found a number of clusters, identified by various colors. Comparison methods can be used to find significant difference of means or variances in two given populations. The comparative techniques are often used to guide the development of predictive models in population health analytics. This figure shows the interaction plot of age, gender, and log transformed cost. The solid line shows the increase of cost in males as age increases, while the dotted line shows the increase of cost in females as age increases. Note that there is a deflection point at the far right side of the diagram where the two lines cross each other. Finally, there are various statistical and machine learning methods to develop predictive models for population health. The common methods are regression methods and classification trees. As discussed in previous lectures of this unit, population health models often attempt to predict an outcome, such as future cost, based on data available in the base dataset. For example, in a simplified model, an analyst may use the current base year's cost to predict the future year's cost. Of course, this is an overly simplified model, where one independent variable is predicting a complex outcome variable. Remember that both of these costs are continuous variables, and log transformations make them somehow normally distributed. Thus, a linear regression can be the model of choice to explore the effect of current cost on future cost. This scatterplot shows the relationship of current cost of a selected population against the future cost of the same population. These cost variables are already log transformed. The extra solid line shows the result of a predictive model, which in this case is training by a linear regression methodology. As depicted, the line includes an intercept and a slope represented by beta 0 and beta 1 in the model. One way to measure the power of this model is to calculate its adjusted R-square. Note, however, that R-squares do not show the hidden biases of errors, thus additional steps should be taken to measure the power of a model. As discussed in previous lectures of this unit, population health models often attempt to predict an outcome, such as being in the top 5% of future cost based on data available in the base dataset. For example, in a simplified model, an analyst may use the current base year's cost to predict the association of patients of a population to the top 5% cost group. Of course, this is an overly simplified model, where one independent variable is predicting a binary outcome variable. Remember that the outcome variable is a binary variable. Thus, a logistic regression should be used to explore the effect of the current cost on future assignment of patients to the top 5% group. This scatterplot shows the relationship of current cost of a selected population against the grouped future cost of the same population. The grouping of the future cost is based on the top 5% threshold. Note that the scatterplot is basically divided into two lines, due to the fact that the vertical axis is only one of the two groups of being in the top 5% and not being in the top 5% of cost. Also, the vertical axis of the plot shows the fact that the logistic regression is indeed predicting the likelihood of being associated to either of these groups, thus ranging from 0 to 1. The added curved line shows the logistic regression model's predicted likelihood of a group association of each patient based on a given current cost. Remember that R-squares are not used to evaluate models that predict binary values, such as being in the top 5% cost or not being in the top 5%. Thus, a receiver operating characteristic ROC curve needs to be constructed, and the area under the curve, AUC, also known as C-stat, should be used to show the power of the model to differentiate the outcome variable. Another common method to develop predictive models for population health analysis is classification trees and various derived models that use such trees. This diagram shows a classification tree based on age and gender as independent variables, and the future cost of a population denominator. The tree starts on the top and branches out as it moves down two other branches. Note that each branch includes a split of the population denominator into a number of categories, based on a certain threshold of an independent variable. For example, in this decision tree, the first branching is based on whether the age of a population is more than 54 or not. Also indicated by the tree is that gender is only significant in differentiating the variance of future cost if the population age falls below 47. In the leaves, N refers to the number of patients in that category, and Y refers to the mean outcome, which in this case is future cost. This concludes Lecture C of Big Data, interoperability, and analytics for population health. This lecture discussed approaches to explore the data such as summaries, histograms, and boxplots, methods to classify the data such as various clustering models, methods to compare datasets such as ANOVA, and finally, methods to predict population health outcomes such as regression, logistic, and classification trees. Note that not all items were discussed in detail. Please see the standalone data analytic component for additional details on methods used for healthcare analytics.